What if I told you there's something in the universe so dangerous that, if it were located halfway between Earth and the Moon, it could instantly wipe out all credit cards, hard drives, and any magnetic device on our planet? And what if I told you that a single teaspoon of this object would weigh more than 1 billion tons? It sounds like science fiction, but it's real. And today we're going to explore magnetars together, the most dangerous and extreme stars in the known universe. Welcome, cosmic explorers, to Cosmic Frontiers. I'm your guide on this fascinating journey through the mysteries of the cosmos. Today, we're diving into the world of magnetars, objects so extreme they challenge our understanding of physics. You'll discover how these stars can release more energy in seconds than our sun produces in 1,000 years, how they are born from the most violent explosions in the universe, and why scientists consider them natural laboratories for testing the limits of physics. And of course, we're continuing our incredible journey toward 1,000 cosmic explorers, each of you making this adventure even more special. Imagine a basketball with the mass of the entire population of Earth compressed inside it. Now multiply that density by 1 trillion. Even then, you wouldn't come close to the density of a magnetar. These objects are a special type of neutron star, the ultra-compact cores left behind after massive stars explode. But magnetars are much more than just ordinary neutron stars. They have magnetic fields so intense that they transform the very reality around them. To understand how a magnetar forms, we first need to imagine the cosmic drama that gives rise to it. When a star with at least 8 times the mass of our Sun reaches the end of its life, it doesn't simply burn out like a candle. It explodes in a supernova, one of the most violent explosions we know of in the universe. During this explosion, the star's core collapses under its own gravity in just a few seconds. It's like compressing the entire core of Earth down to the size of a small city. In this extreme process, protons and electrons are literally crushed together, forming neutrons, hence the name neutron star. But what sets a magnetar apart from an ordinary neutron star is its absolutely colossal magnetic field. If Earth has a magnetic field that protects us from solar particles, a magnetar's magnetic field is trillions of times more intense. To put that into perspective, it's like comparing a lit candle to the explosion of 1,000 hydrogen bombs happening simultaneously. This magnetic field is so powerful, it can alter the structure of nearby atoms. Now, you might be wondering, how can something be so dense? The answer lies in the fundamental nature of matter. In our everyday experience, atoms are mostly empty space. If the nucleus of an atom were the size of a ping-pong ball, the electrons would be orbiting several kilometers away. In a neutron star, that empty space simply disappears. It's like taking a sponge full of air and compressing it into a solid ball, but on an unimaginable scale. A teaspoon of magnetar material would weigh about 1 billion tons, more than the entire global fleet of cargo ships combined. Density, however, is just the beginning of the extraordinary story of magnetars. Their magnetic field is so intense that it creates effects that seem like magic, but are pure extreme physics. Near a magnetar, space itself behaves strangely. Light can literally be bent and distorted. Subatomic particles are accelerated to near-light speeds, creating beams of radiation that slice through the cosmos like cosmic lightsabers. To grasp the intensity of this magnetic field, let's compare it to our everyday experiences. The magnet on your fridge has a magnetic field of about 100 Gauss. A hospital MRI machine operates at around 30,000 Gauss. Earth's magnetic field is only about half a Gauss. Now brace yourself. A magnetar has a magnetic field of about 100 trillion Gauss. The difference is so absurd that our brains struggle to process it. If you had a magnet with just 1/10 the strength of a magnetar and placed it at the distance of the Moon, it would still be able to erase the magnetic strip on your credit card here on Earth. The practical effects of this extreme magnetic field are both fascinating and terrifying. If a magnetar were located 150,000 kilometers from Earth, halfway to the Moon, its magnetic field would be strong enough to cause immense damage to our technology. All electronic devices would simply stop working. Satellites would fall from the sky. Earth's magnetosphere, which protects us from solar radiation, would be completely distorted. It would be like living in a permanent electromagnetic storm. But the story gets even more impressive when we talk about stellar earthquakes, events that might be the most violent phenomena a star can experience. Unlike earthquakes on Earth, which involve the movement of tectonic plates, the stellar quakes of magnetars involve the sudden reorganization of unimaginably intense magnetic fields. It's as if the very fabric of space-time around the star violently reconfigures itself. When a magnetar experiences one of these stellar quakes, the amount of energy released is simply astronomical. In just a few seconds, it can release more energy than our Sun produces in 1,000 years. To put that into human perspective, it is as if all the energy humanity has ever consumed in its entire history were released in the blink of an eye. This energy is emitted primarily in the form of gamma rays, electromagnetic radiation, so powerful that it can be detected by our telescopes, even when it comes from magnetars located in other galaxies. What's most astonishing is that these events can affect our technology even when they are thousands of light years away. In December 2004, a magnetar called SGR 1806-220, located about 50,000 light-years from Earth, experienced a stellar quake so powerful that its effects were felt here on our planet. Satellites were temporarily blinded by the burst of radiation, and scientific instruments had to be shut down to avoid damage. It was as if a gigantic nuclear explosion had occurred on the other side of the galaxy, and still managed to affect our equipment. The discovery of magnetars is relatively recent in the history of astronomy, which makes these stars even more fascinating. The first hints of their existence emerged in the 1990s, when astronomers began detecting gamma-ray bursts that didn't fit any known model. These were events too energetic to be explained by existing theories about ordinary neutron stars. Physicist Robert Duncan and astronomer Christopher Thomson were pioneers in the theory of magnetars in the early 1990s. They proposed that certain types of neutron stars could develop extraordinarily intense magnetic fields through a process called the dynamo effect during their formation. According to our current understanding, during the first few seconds after the supernova collapse, extreme convective movements inside the newly formed star can amplify the initial magnetic field to unimaginable levels. Observational confirmation came when X-ray telescopes began detecting characteristic patterns from these stars. Magnetars emit radiation in a pulsed and irregular manner. Unlike ordinary neutron stars, which pulse very regularly, like precise cosmic clocks, this irregularity is caused precisely by the complex interaction between the extreme magnetic field and the stellar matter. Today, we know of about 30 confirmed magnetars in our galaxy. Although scientists estimate there could be thousands of them, each new discovery teaches us something different about the extreme limits of physics. Magnetars have become true natural laboratories where we can study how matter behaves under conditions we could never replicate on Earth. One of the most intriguing characteristics of magnetars is that they seem to have relatively short lifespans by cosmic standards. Unlike other neutron stars that can remain active for billions of years, magnetars appear to lose their extreme activity in just a few thousand or million years. This happens because their intense magnetic fields gradually dissipate, releasing energy in the form of radiation. It is as if they are stars that burn at maximum intensity for a relatively brief period before calming down. This temporal characteristic of magnetars raises fascinating questions about stellar evolution. If they are so short-lived, how do we explain that we can observe so many of them? The answer likely lies in their formation rate. Our galaxy must produce magnetars frequently enough that there are always some active. This suggests that the conditions necessary to form these extreme stars are not as rare as we initially thought. Magnetars also challenge our understanding of the very concept of impossible. Before their discovery, many physicists thought that magnetic fields of such intensity simply couldn't exist in nature. Quantum theory suggests there's a fundamental limit to the intensity of magnetic fields, but magnetars operate very close to this theoretical limit. They are like natural experiments, testing the boundaries of fundamental physics. Studying magnetars helps us understand not only these extraordinary stars, but also other extreme cosmic phenomena. Their extreme physics can give us clues about how black holes work, the nature of dark matter, and even the conditions that existed in the first moments after the Big Bang. It's impressive how these objects, born from the violent death of massive stars, can teach us so much about the fundamental mysteries of the universe. And here we come to a fascinating reflection on our place in the cosmos. Magnetars show us that the universe is even more extreme and violent than we ever imagined. They exist on a scale of energy and density that makes our human experience seem almost insignificant in comparison. And yet, through science, curiosity, and collaboration, we've managed not only to detect these impossible objects, but also to understand their fundamental nature that is truly extraordinary. Recapping our journey today through magnetars, we've discovered that these are the most dangerous stars in the universe, with magnetic fields trillions of times more intense than Earth's. We've seen how a teaspoon of their material would weigh more than 1 billion tons, and how their stellar quakes can release more energy than the Sun produces in 1,000 years. We've explored how their recent discovery has revolutionized our understanding of extreme physics, and how they continue to be natural laboratories for testing the boundaries of reality. Magnetars remind us that even when we think we know the universe, it always has even more extraordinary surprises waiting to be discovered. Each magnetar is a monument to cosmic creativity, showing that nature can be more extreme and imaginative than any science fiction we could create. Cosmic explorers, I have a question for you. If we could send a robotic probe to study a magnetar up close, obviously from a safe distance, what aspect of these extreme objects would you most like it to investigate? Leave your ideas in the comments, and let's continue this fascinating discussion. And since we're talking about the most extreme mysteries of the cosmos, what cosmic phenomenon would you like me to talk about in the next video? Wormholes, galaxy collisions, dark matter? Leave your suggestions in the comments. Your ideas always inspire our next scientific adventure. We're on an incredible journey toward 1,000 cosmic explorers, and each of you makes this adventure even more special. If this video sparked your curiosity about the extremes of the universe, join our crew by clicking subscribe. Like this video if it expanded your cosmic horizons, and share it with someone who also loves the mysteries of the universe. In the next video, we'll explore another phenomenon that challenges our understanding of cosmic reality. Until then, keep looking at the stars and wondering about the infinite wonders that surround us. The universe is vast, mysterious, and absolutely fascinating, and we've only just begun to explore it.